We'll have the first speaker as Professor Thokozani Majozi. I call him Thoko from South Africa. So he's currently the Dean of Faculty of Engineering and Built Environment at University of Witwatersrand. And he's also a Professor of Chemical Engineering, School of Chemical and Metallurgical Engineering at University of Witwatersrand. And we have been, I know Thoko for a while, I guess, in 2014, 15. So we have been working on multiple projects. Hi, Thoko. So
hi there, everyone. Morning, everyone.
Yeah. So yeah, with that note, I'll leave the floor to you, Thoko. So you'll be the first speaker for the session. Yeah.
Thanks, Chair, and thanks, colleagues, for coming to be part of this workshop. I will then go straight to the presentation so that I save on time. Can you see my screen? Now, which one do you see?
Yeah, slideshow mode, it's fine.
It's not slideshow now. No, thank you very much. So, colleagues, again, welcome to this meeting this morning. I'll just talk about water minimization, mainly in the South African context. I'll have a few case studies here to showcase to colleagues in terms of what we are doing in South Africa to save water. I'll start off with maybe introducing my group quickly. We are, as it has been said now by Babji, I am the chair, I hold the chair in sustainable process engineering in the School of Chemical and Metallurgical Engineering. We work on batch processes, but we also work in continuous processes. Recently, we started looking very closely, that is in the last 5 years or so, we started looking at Water-Energy-Nexus, as you can see over there, but we also include chemicals, of course, in that. So I'm going to talk more about that later. I'm not going to dwell on the other things that we do, but I just wanted to give a sense of what we do. Most of our work is premised on process integration. And in as far as this particular presentation is concerned, what I'm going to do is to just talk briefly about the social perspectives as far as water and energy are concerned, talk about the water conservation methods, and then talk briefly about the nexus, because this is part of this presentation, but nexus in its broadest sense. And then, of course, as I did mention, there will be real-life case studies. The social perspectives here, by the way, it's something that we always have to keep in our minds. We cannot talk about saving water and energy without looking at the social dimension. In fact, that is the reason why we are looking at water and energy. It is the social perspective. Someone did actually mention, this was in 2016 in the Los Angeles Times, that of the fears that have risen alongside a warming planet, perhaps there is nothing that is close now to our attention as the possible water wars. And the issue of water wars, by the way, although people look at it at a distance, we are starting to see it even within the South African context. People are starting to really realize how that issue is. But there are some documented cases here of water wars, just to demonstrate why we are so obsessed with saving water. If you think about India, this is closer to you, colleagues in India, you know very well the Kaveri River. There are two communities there, the Tamil Nadu and the Karnataka. These are agricultural communities, and they've always been fighting along this river. One is upstream and one is downstream. Karnataka is upstream and the Tamil Nadu is downstream. And they fight all the time in as far as water is concerned. In our neighborhood here in the southern part of Africa, but not in South Africa per se, we've got an issue of Botswana and Namibia as well. The more Namibia develops, the less water gets into Botswana because they use the same river stream from Okavango River. And then there's another case here, which is also well documented from Thailand. After the construction of the Park Moon Dam, there were people that suffered downstream because of that. Most of the water was captured by the dam. And then there's an issue of Inkomati River. This is now between us here in South Africa and Mozambique. There's always been an issue as well with the water in that Inkomati River basin. And then in Europe, there's always been an issue with the Rhine River. Rhine River crosses a number of countries until it gets into Rotterdam before it gets into the ocean. And all the time, there has to be frequent removal of contaminated sludge in Rotterdam Harbor. From all the countries that it goes through until it gets to that, but there's been an agreement around that now. Although there still are tensions. And then there's Nile River. The Nile River is here in Africa as well. It's still a hot topic at the moment. It is something that can explode anytime. It involves Egypt and Ethiopia. The mouth of Nile River is in Ethiopia, and it goes all the way past Sudan, and then it gets to Egypt, and then ultimately the Mediterranean Sea. And there's an issue of Ethiopia having constructed a very, very big dam holding all the water to itself, and then having very little water getting into Egypt. So these are cases of why water is such an important resource, and is going to grow in that capacity going forward. And that explains why we are so obsessed with this topic of water and energy optimization. It is very important that we highlight that. It is really something that we ought to be doing, not just for fun, but to address some of the very pertinent issues. If you look at the water scarcity map, the global water scarcity map, which just indicates which countries don't have issues with water and which countries have issues with water. South Africa ranks very high among the countries that are water scarce. Actually, we are regarded as a water scarce country. We rank in the top 30 a list of countries that are considered driest in the world. As you know, there are about 195 countries in the world. So being in the top 30 means we really are very, very high. So that is where we are. So there are two reasons why a country could be water scarce. You've got the economic scarcity, and then you've got the physical scarcity. The economic scarcity is simply saying there is water there, but you have not invested enough to capture that water for adequate use. That is economic scarcity. It's not that there's no water in that country. South Africa doesn't rank in that category. South Africa is a physically scarce country, meaning that the location of the country is such that the rainfall is very, very, very low. We get less than 50% of the average rainfall globally as a country. So definitely we are a water scarce country, and we have to start thinking very, very seriously about how we use our water sparingly or efficiently. If I can just maybe share with you some of the sectors where we use water. It is mainly in the agricultural sector during irrigation. That's fine, but that's not really the problem. The problem is hidden somewhere there, where we say, I mean, if you look at the mining industry, the mining sector, we tend to separate it from your manufacturing industries or your chemical industries, but you can group them if you want to. So I've done that there. I've got mining industry and power generation. If you group all of those together, they consume about 8% of water in South Africa. But what is hidden in that equation is that that water is highly contaminated by the time it leaves those industries. So they use 8%, but they contaminate more than 60% of our water streams. I just have an example that I want to share with you very quickly. I think this video is going to play here. It's a real life case study. As I'm sitting here, I decided to work from home this morning because of load shedding. So I'm at home this morning so that I have connectivity. But a stone's throw away from where I am, there's a river known as Henops River, which was very clean when I came here 15 years ago. It is now looking like what I'm going to show you because of industries. And at the heart of those industries, it is the textile industries next to our airport. I'm going to show you that video now. I hope it's going to play quickly. It's not a very long video. I hope you can all see this. This is the river that was very, very clean not long ago. This is how it looks like now. That is foam that you see on top of this river. There is no life that can survive there. You can imagine what the COD, BOD there is at the moment. You can't find any fish there. There's stench all over that river. And that is all because of industries. It's one of our very, very biggest rivers, or well, it's one of the biggest rivers in the Centurion area. So I felt that I could just share that with you. Let me go to how do I get to the next slide now? I felt that I could just share that with you, just to show how bad things are at the moment. So if you look at the water conservation methods, the one that is very, very predominant in industry is recycle and reuse. So we can say we recycle, we reuse. It's very predominant. It's easy to accomplish. And yes, you can see some of the great reduction opportunities there. I have a simple example taken from one of the case studies that was done in the silicone plating plant. This is in the UK, by the way. It's one of the case studies. It was presented in one of the workshops that we held here, where they worked at this plant for a few months and then reduced water by almost 30% by just exploring recycle and reuse opportunities. This can happen, and we must do this all the time. But if you really want to see some serious or significant reduction in water use, it is when you start involving regeneration. So when you start talking about regeneration, recycle, or regeneration reuse, it is there that you see a steep change in terms of water reduction. But that also comes at a price. And why am I saying this? In fact, it is here that we can start talking about the water-energy-nexus, because you don't talk about regeneration without really thinking about energy. If we see the diagram that I have in front of you now, think of a situation, and I've really simplified it. It's overly simplified. You've got the membrane network on top. That membrane network could be your regenerator of any kind. It could be ultrafiltration, reverse osmosis, electrodialysis, all those membrane systems that we normally use in industry. And then I've got the water network at the bottom there, and they work together all the time. In order to reduce that water, you would have to increase the recyclability of this water here. The more you recycle, in other words, the more you regenerate, the more you recycle. More regeneration means more recyclability of water, meaning that if you recycle more, as you can see, they have magnified these arrows here to accentuate that point. If you recycle more, or if you regenerate more, you'll reduce your amount of water. So you'll reduce the amount of fresh water that you take into the process, and you'll also reduce your amount of effluent. And that's why we use regenerators, but that comes at a price. The more you regenerate, the more energy you'll have to use, which means that the more energy you put into the system, the less water you'd have to use. The less energy you put into the system, the more water you'd have to use. That is the nexus that one is looking at here, which is very much within the process. But of course, we can expand this and look beyond the process. I've got an example here that I'm going to talk about where we go beyond the process as we look into the water energy nexus. Now, the work that we do in our group is really about, we do optimization in the main. It's process optimization. So basically, in very simple terms, we are looking for that sweet spot there, if you can call it that, that spot where your overall cost is minimized because you've minimized your energy cost and you've minimized your water cost. We are looking for that point there. So that is basically the essence of the work that we do in terms of optimization. You consider everything that is involved in the process, particularly within the energy water space. And this you cannot do, by the way, using rudimentary methods. You would need to have a systematic algorithm that allows you to reach that. It's not simulation, it is definitely optimization. We've talked about, since yesterday, we talk of water, energy, food nexus. But I've said in the recent past that maybe we are missing another dimension here, which is chemicals, really. Because you cannot achieve all of these things without chemicals. The chemicals play a very, very, very huge role in the food sector. I don't know how much food crops we can grow without chemicals. To produce chemicals, we all know here, I think it was Raj's presentation yesterday, the amount of energy that is used in the production of chemicals. Even Vanita spoke about that at some point. So the fact that we have chemicals which are very central to our livelihoods means that we will always use energy and water in big numbers. And that's why I'm saying maybe somewhere there, it's still very hypothetical at this stage. In fact, I haven't seen a paper that talks about this, where it's energy, water, food, or energy, water, chemicals together. I always leave out food because that's not really the space that we find ourselves in most instances. But really the full nexus should involve everything that you see there. That's how it's supposed to be in real life. This brings me to energy. If I can just say briefly about energy here in South Africa, what are the sectors that use energy? We've got the agricultural sector again, there's energy used there. Now, contrary to what you saw in water, the agricultural sector used the largest amount of water, but it uses the least amount of energy. That's the flip side of this. And then the residential sector is the one that uses a significant amount of electricity. In fact, this is mainly the energy, looking at the electricity concept, because this is the main energy sink for us, electricity. And then the commercial sector uses about 7%. And then the main or the most significant user is industry. And that is the reason why when we say we want to save energy, the first port of call should be industry. If we say we want to save water, still the first port of call should be industry, because they are the ones who contaminate the most. When we say we want to save energy, it should still be industry, because they are the ones who consume the most. So we are really at the right place as chemical engineers in terms of saving water and energy. And what you see also there's a legend is the energy distribution or the energy profile within South Africa. Most of our energy comes from coal, by the way. Almost 70% of our energy comes from coal. So we are still very dependent on coal, despite the fact that there are calls now to reduce our dependency on coal, because it's not regarded as a clean resource. So we are trying very hard to reduce that. But as it stands now, almost 70% of our energy comes from coal. You can see that in terms of renewables, really there's no appetite in South Africa to move into renewables. We talk about it at length. I think in the next 10 years, that might change completely. Solar in particular has come out as a very, very strong force. And in terms of cost as well, the cost of solar has come down quite sharply, starting to compete now with the fossil fuel. So that might change. But we have a lot of coal deposits, a lot of coal deposits in the country, which makes it very difficult for people to let go of coal. They also talk about clean coal technology. And to be frank with you, I don't think there is such a thing as a clean coal technology in as far as carbon dioxide is concerned. If you want to burn coal, you will produce carbon dioxide regardless of how clean it is. So then this brings me now to really the heart of my presentation, which is the case studies. If I can just share with you some of the case studies based on some of the work we've done here in South Africa. South Africa is a highly industrialized country. In fact, the most industrialized in Africa. So we've got a number of industries here, multinational companies from all sectors, really. What the example I have there is from the Pulp and Paper company, which is SAPI. SAPI is the South African Pulp and Paper industry. It's a multinational. I think you would know SAPI as well. It's one of the biggest pulp and paper manufacturers in the world. It's a South African company. And we were asked, they've got a facility not far from here. In fact, if you saw the floods on television not long ago, this is actually where this plant is. It's just next to the ocean, a place known as Umkomas. It's called SAPI Cycle at Umkomas. We did some work for them there. They wanted to reduce water in their bleaching facility. When you make paper, you have to have bleaching at some point. That's why you have your white pages in particular. Your cut box is a bit dark because it's not bleached that much, but your paper that you write on is white because it's bleached using chlorides in particular. So it's a very, very important part of the plant, the bleaching plant, and it uses a lot of water. The idea was, how do you reduce water there then by taking all options into account, including regeneration? What I'm showing to you there is an outcome of a number of weeks, if not months, because when you do this exercise, the first thing that you do is to identify your sources of or potential sources of reuse water, as well as your potential sinks. The blue arrows that you see there, those are what I would call sinks. Basically, the blue arrows, this is the water that is being used in those unit operations over there. So you use water in the washer, use water in screening, use a lot of water, as I said, in bleaching. The red arrows that you see there, you would call that your potential sources of water. So basically from screening, we can produce water that could be used elsewhere in the plant. As to where exactly and how much of that could be used, that is what we leave to optimization. from the stripper as well. You can use that water that comes from the stripper elsewhere in the plant. Also, these are the both strippers. From bleaching, there is an amount of water there, and significant amount of water, by the way, that we can use elsewhere in the plant. And with this information, we need to have then your flow rate. We first identify these potential sources and sinks. The second step is to then get the information on the flow rate of each of those streams, as well as the composition of each of those streams. So I always say when we do this exercise of water minimization in plants, because we do this now on a regular basis. In fact, there's one project we are working on now with South 32 in Richards Bay, doing the same thing. The first thing is to identify your sources and your sinks. And this can take about 70%, 60 to 70% of your project time. It looks very simple when it gets to this stage, by the way. There's a lot you can do beyond this point. But to get here takes a very, very long time and a lot of buy-in from the engineers within the plant. Because all this information that I'm showing to you now, which is your flow rates and your composition, that is what you are given by the engineers who work in the plant, who understand how much and what composition it is. How much goes where and what the composition is. So you have to work with the people in the plant, and then you'll then discretize your plant into the sources as well as your sinks. When it gets to this point, then it is here that you use your mathematics. I tried very hard for this presentation not to show too many equations. In fact, I tried to avoid equations for this presentation, just to show you the concepts rather than the equations. So we build a mathematical model from here that will definitely take advantage of the recyclability and reusability of water. And in those models, we can also embed regenerators. We've done that in the past. I can share with you some of the papers that we've written in that regard, where we've looked at ultrafiltration as one of the regenerators. We've looked at reverse osmosis. We looked at electrodialysis, by the way, which is something that is not as common as reverse osmosis in South Africa, but it's a very powerful regenerator. We've also used at membrane distillation. So we're doing some work there on membrane distillation as well. These are all the types of membranes that you would use as regeneration. So once you have this information, then really you put it into the model, and then you can come up with the plant. This is one of the results that we came up with. And this is the good thing about using mathematical optimization. You can always, play around with different variables and different options. And you always can provide different avenues for companies to decide which one is cheaper, which one is doable at any given point in time. What I'm giving you there was the best solution that would require the use of an electrodialysis. Now, this is very, very expensive. I mean, to put a regenerator in the plant is very, very expensive. Not just in terms of energy, but in terms of the capital cost that you have to invest in that. So you always have to factor that in. There's an issue of the operational cost because of energy, but there's an issue of capital cost investment. But the payback tends to be very, very, very short. Usually you have a payback period of less than 2 years in most of these projects, which is not a very bad payback. In most industries, they tend to be worried when you go beyond 3 years of payback period. So this is a doable project. About 36% reduction in water, in fresh water, and about 60% reduction in wastewater because of a regenerator. One thing that, by the way, I don't mention here, and we don't mention it in most of the work that we do, is that it is not just the wastewater that we account for here. We say 60% reduction in wastewater, but there's also brine that comes with the regeneration. We seldom ever talk about that. So it's not really effectively 60% reduction. I would say maybe effectively you are sitting at about 40% reduction in wastewater if you count brine that would come from the electrodialysis unit. So we've worked with the pulp and paper industries. They use a lot of water, and we are still continuing maybe to explore avenues of working further, because this was just one unit. And one of the things that came out of that project, by the way, was that you could actually have a zero effluent facility. That is one facility that can have zero effluent, because some of that water they had a sink in the operation. They could actually afford to do that. There's another example here. We have Johnson & Johnson, which Johnson & Johnson is not far from, maybe it's too far from where I am. It's in East London. East London is one of the cities in one of the provinces. Eastern Cape here in South Africa. It's also a highly industrialized province, by the way. The biggest Mercedes assembly facility is down in East London, Mercedes-Benz. But they also have Johnson & Johnson there. Johnson & Johnson, as you know, is a pharmaceutical facility. They make shampoos in that facility. They make deodorants, they make soaps, they make lotions in that facility. We worked in that facility about what now, maybe 6-7 years ago. The idea again was to reduce water. I've just given you the layout of how the facility looks like. They receive water from the municipal supply, and then most of it will be used for cleaning. And then they'll clean the mixers and the holding tanks. They'll also use it somewhere in heating and cooling. Some of it is deionized because, of course, I mean, you are dealing here with the pharmaceutical facility, so your water must be of cleanest possible standards. So they'll deionize that water, but there's also water that they would use, of course, for general domestic purposes like drinking and, of course, ablution facilities. So we're looking at this mainly, the mixers and the holding tanks. I have a nice picture here that I want to show you. Some of you might identify with what you see there. Wherever you are in the world, that's the power of being a Johnson & Johnson facility. I'm sure that you can guess what this is. This is Johnson & Johnson's baby lotion. This is a baby lotion there. And it's anyone would know this, would identify with it. So what happens really is these are the tanks where that lotion is manufactured, and then they discharge this lotion from these tanks. After discharging, this is what is left behind inside the tank. And very interestingly now, this is still a good product, by the way, but there's nothing you can do now. I mean, gravity has done its part, and then because of the nature of the product in terms of viscosity and the adhesiveness, you can't really remove that, you know. Now what they do is they spray these tanks with water, clean water from the municipality. They spray these tanks, all that goes into the drain. Now this is still a product that goes into the drains. When we visited that facility, on my first day at that facility, I realized that there was a good opportunity for saving water. They just spray this and all of it goes into the drain. And then we had to then see what are the avenues of reducing that water. Some of the results. And again, before you even go there, you need to get a lot of information from the people who work in the plant. You also, as a scientist, have to spend time in the plant. I have a nice photo that I took in that plant. I don't have it with me here. I spent a lot of time in that plant as well. So they make shampoos, as I said, deodorants and lotions, and then we know this comes from the plant, that after they've produced the shampoos, how much is left in the tank. This is the residue. This is the degree of contamination that you have in the tank. It's important that you know this in order to determine recyclability, because you don't want to tamper with product integrity. If we say we're going to reuse water that is contaminated, it must not contaminate the next product in the batch. This is a batch facility. That's also another dimension, which makes it very, very complicated. So each of those tanks will produce different materials. So what each of those tanks will produce samples at some point, it will be making deodorants at some point, creams at some point. So you have to make sure that the cleaning is really done properly so that there is no element or opportunity for cross-contamination, which would of course affect product integrity. So quality there is of essence. So all this information would come from the plant. And then they'll tell you also what is the maximum outlet concentration of water that they produce. In other words, after they've sprayed and that water has to be dispensed with, it has to go into the nearby river stream, how much concentration is allowed. So all this information is given. And then, of course, the amount of water that they would use when they clean. The CIP there is a very common term that is used in almost all batch facilities. It's called cleaning in place. So even in the textile industries, they've got CIPs there. So they would clean, this is the amount of water that they would use in cleaning each batch. After each batch, this is the amount of water they'd use to remove whatever residual products is there. And then, of course, they would give us the number of batches that they would have to produce in a given period, and also how long it takes within the tank to produce this. This is the issue, by the way. When we're dealing with batch plants, you cannot avoid looking at time. So this is the time dimension that they gave us as well. And these are the results that we got. Here in this facility, we saved water by about 20%, fresh water, And then there was 30% product recovery. It was important that I give you that perspective because it's difficult to understand where does product recovery come from now in this context. But with the background that I've just given you now, that you leave some of the product in the tank, you spray the tank in order to clean it for the next batch. That water that you spray in there leaves with the product. And then we realized that by recycling that water back into the facility, some of the product could actually be recovered because most of these lotions are aqueous based. So in any event in that tank, you'll be putting water. So if you recover some of the streams back into the tank and then top it up with water before you do the ultimate formulation, you recover quite a number of products there very, very easily. So there was a 30% product recovery, and that was associated with almost 3 million rand per annum that was saved in that project. They still do that, by the way. You know, I'm still in communication with them. So this is equivalent to about $200,000. And as I say, this was some time ago, maybe more than 6 years ago when we did this. It would be now of greater value than that 3.7 odd million rands per annum that they were saving. So it's another example. And then lastly, I just want to share with you quickly one example. This is based, another example on ESKOM. ESKOM is our largest power generation facility. They've got about 15 of very huge power generation facilities in the country, old style facilities, which are based on pulverized coal power generation. So it's just a boiler. You put in coal there, you boil the water, you steam it up, and then you superheat your steam, you run your turbine, and ultimately you have your electricity. There are 15 of them in the country. We were asked to look at one in particular, which is in Kriel. Kriel is in Mpumalanga. Mpumalanga is another province here in South Africa. So this is a 3.6 gigawatt facility. South Africa as a country is a 43 gigawatt facility. So this will give you a sense of how big this facility is. That's more than 20% or almost 20% of the national capacity that you would require. So it is a huge facility. They use a lot of water in that facility. So this is the facility. You've got cooling towers over there. This is the cooling towers over there. And then those are your stacks. This is the stack where you produce your gas, your gas after burning your coal. This is your flue gas. I always say to people, the red part, this is deliberate, by the way. I've got red there and I've got white there. The red part is what will kill you. This will kill you. The white part is what won't kill you. This will take a very long time to kill you. It will kill you also because there are no ions in that water that you see coming out of that. So if you drink that water, you'll be deionized after some time, but it's not as bad as what you see over here. So this is how the facility looks like at Kriel. We're asked there to come in and save water, but where does the water come in power generation? Quickly, what you see there is the generation facility. So there is your stack that I just showed you now with flue gas. There is your cooling tower that I've just shown you now with your evaporation there, which is the water really. This is water over there, evaporating water. But because of that loss of water through evaporation, we have to make up all the time. So we use fresh water here. This water comes from municipality at times, or this water can come from the rivers in most instances to make up for whatever loss you have there. You need that water all the time so that you cool the exhaust from the turbine. So your coal goes into the boiler, like I did mention, you need air, of course, in order to burn that coal. And then, of course, the flue gas goes out. After burning the coal, this is your water, this is a closed system that you see there. Your water will boil as it goes through the boiler. It will be superheated as well. It must be superheated. And then it goes to the turbine to generate your electricity. The exhaust from that turbine has to be cooled at all times so as to improve the efficiency of the plant. If you don't do that, the efficiencies tend to drop very low. And here I'm not talking about very large efficiencies, by the way. The highest efficiency for a plant like this is 35%. You cannot go beyond 35% in terms of efficiency. But be that as it may, if you remove this water here, this cold water, that problem will be even more. In fact, you'll be operating easily at maybe 20%, which is not a good thing to do. So you need this water. And how much are we talking about? We're talking about huge amounts. I'm going to give you the figures quickly now. I'll be closing. I just want to draw your attention to the sources of water in this plant, and I'll just tell you how the plant looks like. So you've got Usutu River. Usutu River is one of the largest rivers we have in the country that feeds the cooling towers. You also have Val River, which is also one of the very, very huge rivers. So in this facility, the krill facility, you've got what we call the northern section of the cooling towers. That's the major water sink. And then we've got the southern section of the cooling towers, another major water sink. The southern part is fed by Val River. The northern part is fed by Usutu River. This facility uses in excess of about 100 megaliters of water a day. It's one facility. I said there are about 15 of them in the country. Then we can do the math in terms of how much water we use in generating power in the country. I've just said to you earlier on that we are a water scarce country, which means that if you say you want to produce more power in South Africa, we are saying we're going to get water from somewhere, but we don't have this water. That is the reality that we have in the country. So we did the same thing, separated this into sources and the sinks. Now, this is very recent, by the way. We did this one, I would say maybe 2016, 17, thereabout. I was already at Wits when we did this work, still very fresh and in the mines. And then this is you split it into sources and the sinks. The variables there, these are the limitless, or I would say that near infinite supply of water. That's why we said that these are variables. This water will always be available from those sources over there. Of course, for mathematical purposes, we know that that's also finite. So we separated this into sources and the sinks. And then we also had to get this information, like I told you, working with the engineers in the plant. They gave us the flow rates. They gave us the concentrations. Here we worked with TDS as a collective measure of contamination, total dissolved solids. We worked with that here throughout. So we have all the information, all the units that generate water, all the units that use water. Ultimately, we came up with this solution here. And this was very interesting. This solution was actually, it was about what, 10%, 20% reduction in water.
Toko, in the interest, sorry, Toko, sorry to interrupt. In the interest of time, can you wind up in 2 to 3 minutes? Yeah.
Okay. I will do that now. I was doing it yesterday. Now it's happening to me. Now you can see that is where we saved water. In fact, it was taking blow down from the northern side into the southern side, because the cycles of concentration on the northern side were much lower than the cycles of concentration on the southern side. So there was an element of recyclability there. And then in short, I told you, so they were using about 120 megaliters of water. And then with the solution that I've just shown you, you can see came down to about 97 megaliters of water. There is a measure they use, by the way, in these units. There is L per USO. This is the liters of water you use per unit sent out, which is the gigawatt hour. So they were sitting at 3.1, and now they're down to 1.9. Again, this solution, by the way, was applied. I'm just giving you some examples of where we've applied this in real terms. That should be the end of my presentation, but I just want to make some advert a bit and say to you, there's a book that we produced out of a workshop that we ran here at VETS in 2016, where we've got a collection of case studies all over the world. So these are the participants from that workshop, and the contributions into that book, by the way, are from really all over the world. The red that you see there are the countries that contributed to that book. We also have other books on batch processes, which will be work on pharmaceuticals, agrochemicals, and the like. So those are some of the books that we produce in the group. And then with that, I'll say also, maybe I must acknowledge the funders, NRF Water Research Commission, and British Council, by the way, which funded us for that particular workshop, and SASOL as well. And thank you very much for indulging me. I'm very sorry for taking much time, but that's what happens in this space. Okay, so thank you.
Thank you, Toko. Thank you so much for a wonderful talk. We